Thank you very much for inviting me. It's beautiful here. Happy birthday, Roger and Sylvia. I understand this is actually Roger's birthday, so happy birthday double to you. And may you have another 150 wonderful years. I'd like to see a lot more mathematics over the time. So I will be speaking about joint work with Taiha and Louisa Fooley, and so everything today will be joint with them. And I did prepare slides, which I'm not giving. I'm sure you'll be happy about that. But if you want a copy, they're there and ready. And so if you don't take notes and you want a copy, there is a copy that I'm happy to send you. If you send me an email, I'll respond and attach them. If we get to them in the end, there's some examples that I'll pull up on the slides. But other than that, we'll do a board talk. And that should keep me from going too fast. But if you have questions, please interrupt. As the title says, we are in a polynomial ring. All right, there goes the chalk already. All right, maybe we will be doing the slide talk if I run out of chalk. All right, I will make sure I do big letters. There we go. All right, so we will be in a polynomial ring. I is an ideal. And for the big picture, it does not need to be monomial, but it will quickly become monomial using initial ideals. So for part of the talk, it will be a monomial. And the goal. We want to find a lower bound for the depth of R mod I. Now, since Graham assigned homework, I'm going to offer bonus and extra credit. So you get bonus if the bound is combinatorially interesting. And I'll explain what that means in a minute. I'm going to go through this board fast, aren't I? And there is a way to even get extra bonus that we'll fill in a few minutes. So what do I mean by combinatorially interesting? All right, there's a lot of ways to measure depth. So some of you might prefer looking at X or TORs or local cohomology. Any of those things are fine. The focus on this talk will actually be looking for regular sequences, and that gives you the depth. But regular sequences are really hard to find. So we need to do something else, okay? So an ideal outline of what to do to find the depth would be, there's a lovely fact that says the depth of R mod I is at least the depth of R mod the initial ideal, where you can choose whatever term order you want. So the ideal outline would be to form the initial ideal. All right, now I can say what I mean by combinatorially interesting. That is a monomial ideal. And there's ways to represent that combinatorially, whether it's square free or not. And so if your bound is interesting to the people who look at the combinatorics, that's where you get the bonus points, okay? So you'd form the initial ideal. You'd use known bounds. Well, we get into a problem right away. Most of the known bounds are for edge ideals of graphs. And that's a very special class. So it's not going to work right now. So the edge ideal of a graph, if I have x1, x2, x3, the ideal would be generated by the products of the variables in the edges. So that would be an example of an edge ideal of a graph. So most of the known bounds are for edge ideals of graphs. There is one known bound that works for any square-free monomial ideal. That is an epsilon or edge-dominating bound done by Dow and Schwegg. And it's the minimum number of edges so that every vertex is adjacent to one of those. And that works, you don't have to be in a graph. It can be any square-free monomial ideal. But that's for square-free. So if you take the initial ideal of, there's classes where you'll get square free, but in general, you're not going to get a square free monomial ideal. So you might want to then polarize. Now, ideally, you don't have to when we're done with this talk, but you might want to. Now, polarizing means suppose I have something generated with a generator that looks like x squared y. I add variables to account for the powers. So I can't, see? K is an arbitrary field. Mm-hmm. It doesn't have to be. It does not have to be homogeneous. And when I take the monomial ideals, the generators can have arbitrary degrees mixed and matched. Okay? So when you polarize, you add variables. So then you'd want to find the depth of the square free thing. There's a known bound for that, which is generally much lower than the number of polarizing variables. And so it gives you a lovely negative bound for the depth, which doesn't work. So what's needed is a brand new bound. Now, there's a lot of bounds out there for graphs. Lots of people have tried to extend them and gotten stuck. It hasn't worked yet. Most of the known bounds have used one technique. They've been using short exact sequences. So there's a standard short exact sequence. Oops. There's a standard short exact sequence plus the depth lemma. These are, when you're in the square-free monomial case, these are smaller, and you can use induction. So if you're wanting to go further, if you have to do work with students, you can narrow your class and give them a known tried and true technique, and you can get work that students can do, but you're narrowing your class, and what we want to do is broaden your class. So what you need is a brand new technique. And that's what I'm going to try to talk about for the rest of the talk today, is a new way to do this and a new technique. And it's going back to the idea that depth can be measured by regular sequences. So if you could actually find the regular sequence, you'd know the depth. But finding regular sequences is really, really hard. So the bonus points, where'd my extra bonus points, come if you find a regular sequence or approximation. So if you can find an approximation of a regular sequence, and that's what we're going to do for the rest of the talk. Now, some things to remember. I come from a world where associated primes are very interesting objects, particularly for things like powers of ideals. Associated primes localize. So if you're looking for embedded associated primes in the square-free world, all you really need to know is when the depth is at least 1 to know when the maximal ideal is not associated, and then you can play games with localization back and forth. So ideally, I want to find as close to the actual depth as I can, but there are settings where if I can even figure out the depth is 1, I'm really interested in that, because it gives you a sub-piece of your bigger picture that cannot be the core of an embedded associated prime. So there's a lot of things going on in here. So looking for these regular sequences and also keeping in mind that sometimes 1 is a really good result. Okay? So that's the rest of the talk, or the rest of the idea. Key point, I did that, I did that, I did that. Oh, so one thing, if you look at a lot of the literature out there, it's about half and half, depth or projective dimension. And that's, of course, because of the Auslander-Buchsbaum formula. But because I am interested in these regular elements and regular sequences, everything's going to be said about depth. But if you come from the projective dimension is interesting world, you get the same result, just flipped with the Auslander-Buchsbaum. Okay. So that covers part 1 of the talk, which the back row can't read, but I put my outline up there to see how big I needed to write, and the answer was bigger. So what we're looking for is a bound that is at least good enough not to give you a negative answer if you polarize. You can still do that first step. You can still take your ideal and form the initial ideal. Now, you may or may not be square free, and you want to see what happens. So if you're going to go for a regular sequence, the first thing you need are regular elements. So I'm going to draw a picture first and then give you a definition, because it's really easy to see what's going on from the picture. So it turns out if you have square-free monomial ideals, regular elements abound. There's lots of them, and they're pretty easy to find. So here's an example of a graph. Pick a vertex, any vertex. I'm going to pick that. Oh, I've got colored chalk. Now the back row will have to tell me if they can see the colored chalk. I'm going to pick this vertex as my center, and then I'm going to look at all the neighbors. Now I'm pretty sure the back row can't see subscripts, so I'm going to label these with A, B, C, D. And when you add that up, you get a regular element. If you take a vertex, pick a vertex, any vertex, take its neighbors, add them up, what you get is a regular element. There are other types of regular elements as well. I'm going to call these stars, because if you look at the picture, it looks like you've got a little star in there. And this works for more general square-free monomial ideals, even better. So this is one of the few results I know that actually works better when you have higher degree generators. So this thing up here is supposed to be a solid generator of degree 4, and this is supposed to be 3 generators of degree 2, and 1 generator of degree 1. And you can play the same game. Pick a vertex, any vertex. You don't necessarily have to use all the neighbors. You just need to use enough neighbors so that every edge is covered. So for this vertex I picked, this edge only has one choice. But these two edges have 2 choices. I could either use both of the bottom vertices, or I could just use that one right there. So if I again label these, you get A plus B plus C is regular on R mod I. And I'll again call that a star. Now, I've drawn these examples for square-free monomial ideals. You don't actually need square-free monomial ideals, but it's a whole lot easier to draw the picture. What you need is that the neighbors are square-free. So you need a center, and it can have various powers and various generators of your ideal. And for every generator that contains that center vertex, there needs to be a neighbor in there, and those neighbors need to be linear in the ideal. Okay? So you don't need your whole ideal to be square-free, just pieces of it. So if you do need to polarize, you can polarize a lot less and add a lot fewer variables. So that gives you something a lot closer to the actual depth and less to expand beyond. So the theorem is that these stars are regular if the neighbors are square-free. And by regular, I mean on R mod I. By neighbors, I mean the representative set so that every edge is covered. And I'm about to. Okay. So what that means, I'm actually going to show you the proof which actually shows you what that means. What it means is that this type of sum, where I have a center and neighbors where every edge is covered by one of these neighbors. So here A is contained in 3 edges, and every edge contains one of the blue vertices. So there's my center and my neighbors. All linear sums of this form are regular on R mod I, as long as these pieces are linear in your generating set of I. Let's not use coefficients. It ends up, I want to put these together in sequences, and it ends up making it very clean if you don't use coefficients. You don't. You can polarize and come down again, and you won't need coefficients. So it's very nice. Have I gotten to your question yet?
Well, I think probably part of the problem is I don't know what polarize means.
Oh, polarize. Let's suppose I have an ideal like this. I'm not linear. I can add variables to my polynomial ring. So I need an extra x, so I'm going to call that x1, and I need two extra x's. I'm going to call it x1, x2. And now my ring is, instead of just a join xy, z, I'm going to add these extra variables. And it's a theorem that the depth of R mod I is equal to the depth of this polarized ring minus the number of new variables. Okay? So over here, I've drawn all my pictures as though they're square free because it's easier to draw the pictures. But in the actual result, I don't care. So here, for example, you've got an edge ACX and an edge ACY in the ideal I. I don't care if I put powers on, so this is this edge and this edge. I don't care if I put powers on anything except the C. The C needs to be linear. But the other things can have powers if they want to in your ideal. But the C needs to be linear in your ideal. Okay? And if the C is not linear, you can polarize to make it linear, but you've added a variable, so you'll need a longer regular sequence when you're all said and done. Okay? So the proof I could actually leave as an exercise because it's fairly follow your nose. You're going to multiply. Oh, I use terrible notation. I've got to use subscripts. I'm so sorry. I hope the back row can see the subscripts. I'm going to make my center B0 and my leaves B1 up to BT. So this is my center. And these are my neighbors. And I can state this very carefully that you've got B0. Every monomial generator of I that's divisible by B0 is divisible by one of these B's, and the power of the B is 1. And that's what that means. That's literally the conditions. So you multiply and assume you land in I, and the goal is to have this thing in I to be regular, and you follow your notes. You multiply F1 times B0. And you have a choice. That's either in I or it cancels. If it's in I, there's a monomial of I that divides it, and so there's one of these B's that divides it. If it cancels because it's monomial, it has to cancel with something that looks like that, and so this Bj divides it. So in any case, you get a B that divides the F1. So then you multiply F1 times the B that divides it. If you're in I, since the monomials of I generating I are linear, this Bj can't help you because it already divides F, and so you're in I, which is the goal. If not, you cancel. If you cancel, I'm running out of subscripts. You get that Bj squared has to divide this Fk, and so then you play the game again. Every time you either land in I, which is your goal, or you push the power up. Everybody in sight's finite. You can't push the power forever, so at some point you land in I. And writing down those details is very basic, but that's the sort of overview. So you literally, to show it's a regular element, just multiply and force your multiplier to be an I. All right, so that's regular elements. This is not the only type of regular element. Okay? There are others that work fairly nicely as well, and more or less the same proof works. The one that ends up giving us some nice things, I'll draw this in a graph, but it works in a hypergraph. If you have two leaves, so A and B are leaves, meaning one generator. And you'll notice the distance here, I take 3 edges to get from A to B. That in graph theory land is the distance from A to B is 3, and it just means that there's 3 edges on that path, and then you get that A plus B is regular. So that's an example of a different type of regular element that actually does play nicely with these stars. Okay? So what you're getting in every case is a linear sum that is regular. So now you have a problem. You need to glue these together in sequences. So you can start your outline. You can start with I. You can form the initial ideal. You can find a regular element, and you do it by just picking a vertex and playing that game. Well, now you need something that is regular on the ideal you get by adding your first regular element in. Well, you have a problem. You figured out how to find regular elements on monomial ideals. This is not monomial. So I'm going to do something that should make everybody in the room roll their eyes and think this is impossible. It's not. There's a theorem to show it's not impossible, but it should look impossible. You're going to form the initial ideal. I'm going to get tired of writing this very quickly, and we're going to give things names. And now I have a monomial ideal. So then I'm going to find a regular element, and then I'm going to repeat. By the time I'm done, I will have taken an awful lot of initial ideals, and it's even worse than it looks, because I've never told you what the term order is that I'm using when I take my initial ideal. Well, it can change at every single step. You can use different term orders all the time. So we'll make a definition. A sequence is initially regular on R mod I if Fi is regular on R mod I sub I, where I1 is your first initial ideal, and for higher i's, I sub I is your next initial ideal. And that looks horrible. That looks awful. And every one of these initial ideals could use, theoretically, a different term order, which looks terrible. Okay? Now, the good thing is, And this is really just a corollary of that result I started with, that if F1 through FR is an initially regular sequence, on R mod I, the depth is at least R. So if you can find an initially regular sequence, you have bounded the depth. The better thing, I'm going to run out of time. The better thing is if I start with I, and I find the disjoint stars, on the initial ideal, I get an initially regular sequence. One initial ideal. You hand me your ideal. I take one initial ideal with any term order, and this is with respect to the right term order. Any term order you want, you take your initial ideal. Once you have that initial ideal, you form as many disjoint stars as you can, and what you get is an initially regular sequence and a bound on the depth. The bound you get on the depth, if you start with a graph, it's comparable to all those family of known bounds. It's about the same, and you can improve it by allowing things like leaf pairs and get better. If you start with an arbitrary monomial ideal, you get a depth bound, even if you're not square free, which wasn't before. If you start with a square free monomial ideal, you get a depth bound that is actually quite a bit better than the only known bound in existence, because there's a fine tuning that I haven't shown you yet. I want to draw a picture to show you the example. There's a fine tuning that lets you guarantee that you will find an initially regular sequence that is at least as large as the number of polarizing variables if you started out not square free and polarized. So you are guaranteed not to get a negative bound if you go that way. So you get something. And then if you can get one more, you suddenly get information about associated primes and all of that. So everything else is examples, because at this point you're probably all saying, oh my gosh, how would you do this? I should also mention that if you reduce to the case of a graph, looking at these stars corresponds to a known bound that is very well studied in graph theory. It is written alpha 2. It is called a 2-packing. It is called a closed neighborhood packing. It is called a maximum distance 3 set. So there's all these different names that end up being equivalent to each other. And so those things are well studied in variance, which means immediately you get that that invariant is a lower bound on the depth for free. But then you can improve it by allowing these other types of things to be glued in. So the rest of the talk is supposed to be examples, because otherwise, how do you know what I'm talking about? So if I go back to this graph, and in all these examples, the depth bound I get is actually an equality. There are examples where you don't get equality, but I'm going to show you the ones where you do. I mean, might as well. I can choose that as a center, that as a center, and that as a center. And so I get 3 regular elements. Oh, let's see. White chalk. I will get A plus its neighbors, F plus its neighbor, and H plus its neighbor. 3 elements form an initially regular sequence in any order you want. And that gives you the depth is at least 3, which is an equality. It's better. If I ordered these differently, you actually get a regular sequence, not just an initially regular sequence. Anytime you have a sum of 2, it will be a regular element, and you can glue as many as you can together to get a regular sequence. That's why I showed you the leaf pairs earlier, because they're sums of 2. Sums of 2 are extra important. Okay? If I show, it's a little more interesting when you don't have a graph, because that's where you have degrees of freedom to choose. And then this is the tetrahedron. I'm going to call this E, F, G is that thing in the back. So this, you've got E, F, G, H, D, E, A, B, D, A, C, D, A, B, C is your ideal. I'm going to start over here. There's only one edge containing F, so I only need one other thing to add to it. Now, something I didn't tell you, because I want to get to one more example before I run out of time, is if there's only 2, you can use this one as your next center, and you can repeat. That was what Aaron asked earlier about, can you go down and do you need coefficients? You don't, because this essentially is a polarizing of e to the 4th. And as you work down your polarization, you can reuse things, and you'd end up not needing any coefficients at all. So you could then do G plus H, H plus E. Well, now I'm stuck, because there's nothing to add to E that would represent this edge. But I can come over here, and I could do D plus A. Every edge containing D contains A. Now I can reuse A because there's only 2 here, and I get A plus B plus C. A is in 3 edges, but every one of them contains B or C. That is, again, an initially regular sequence that happens to also be a regular sequence, because these pieces are disjoint. These are 2, or actually there's 4 things of 2 and 1 more. And when you have things of 2, you can always go 1 further. So that is actually a regular sequence as well. And sure enough, depth is 5. Lots more examples where your initially regular sequences are actually regular sequences. But there are some examples where they're not. And so figuring out exactly where that boundary is something that is ongoing research. Now, I'm running out of time. Pardon? I've got 5 minutes? Oh, good. Okay. So I want to do some examples that are not starting with monomial ideals and edge ideals, because that's kind of the whole point. So some people in this room study things that come from Reed-Muller codes. So if you don't know what a Reed-Muller code is, that's okay, because we're about to get away from it, but you can represent them as projective varieties over finite fields. And you can look at the ideal defining that, and there is a known Grubner basis that's binomial, which makes it really easy to find your initial ideal. And what you get is what's called the edge ideal of an oriented weighted graph. Now, at this point, I was going to pull up the screen, but I think it may take longer to pull up the screen than to just draw my picture. So I'm just going to draw the picture here. I drew it out ahead of time. So there are quite a few papers popping up about edge ideals of weighted oriented graphs. And if you've wondered why, I just gave you the background. And I think Aaron Simies probably knows a whole lot more about these than me, because I've seen you on some of those nice papers. Raphael. Yeah, Raphael, that's how I got into it, was through Raphael. So an oriented weighted graph, I'm going to start with a triangle with whiskers for a very specific reason. And you put orientations on your edges. And these go out, these go in, these go out. And I need to label these now. I'm so sorry, but I have to use subscripts. In the inner part, I'm doing x1, x2, x3. And then on the whiskers, I'm going to do y1, y2, y3. And then you put weights on some of the vertices. I'm going to weight these bottom 2 vertices as 2s. Now, the trick is you start at the base of an arrow. So let's look at this one first. And you go to the head of the arrow, and if the head of the arrow has a weight, you use it. If the base of the arrow has a weight, you ignore it. Okay? That's that arrow. I'm going to go around the triangle next, so I'm going to get x3, x1 squared, x1, x2. I don't have a square on x1 because it's the base of the arrow, not the head. x1, x2, x2, x3 squared, and then I had two more, x2, y2, and I did y3, x3, x1, y1. So this is the edge ideal of a weighted oriented graph. It is not a square-free monomial ideal, but it is monomial. It is the initial ideal of the defining ideal of the projective variety that is a Reed-Muller code. So it's actually coming from someplace non-monomial. And it is classified, it's already been classified, that was with Raphael Villarreal and some other people, when these things are Cohen-Macaulay if you start with a whiskered graph. And I have taken one that should be Cohen-Macaulay, and I flipped one arrow around. And that's where this example comes from. So what can you say about the depth? Well, the first thing is it's a little bit easier if you go ahead and polarize this one. And because there's already so many subscripts around, I'm going to use A and B as my extra variables because they're letters I haven't used yet. So x3 is going to get B, and x1 is going to get A because 1 comes before x1, x2 squared. Oh, I guess just x2. Okay, there we go. I put the 2 in the wrong. I was thinking, oh no. X2, x3b, x2, y2, and I'm running off. Some of you probably can't see that, so homework, you get to figure out what it is. And then I wrote down a regular sequence so that I wouldn't have to look at it. But let's look here. I'm going to start, I'll draw it in a minute. I'm going to start with y1. Because it's a whisker, you only have y1 in one edge, so you can do y1 plus x1. You can do the same for y3. But then I can reuse x2, and it works with those two edges. There is a way to draw the picture so that this makes sense. So first of all, I used my 3 leaves as centers because that gives you a lot of power. And then I was allowed to reuse x2 because I only had 2. And you'll notice that anything containing x2 ends up also containing A or B if I wrote all my subscripts in the right place. If I didn't, homework problem to figure out where I wrote a subscript wrong. You can actually end up seeing these powers as sort of an extra edge extending out, and then some of your things swing around that extra edge and some don't. So you can visualize these to find them fairly easily. Sure enough, that gives 4. For the polarization, I had 2 polarizing variables, so this gives depth at least 2. Now, since I told you I started with something that was Cohen-Macaulay and flipped an arrow around, and this thing has dimension 3, you can now probably figure out fairly quickly that the depth is exactly equal to 2, rather than just greater than or equal to, because it's not Cohen-Macaulay and it's dimension 3. So these things work pretty well. 2 other examples that now I see that the clock says I have to stop. So 2 other examples where you can work things out like this are Riesz algebras of edge ideals. If you go back to 1990, Raphael figured out that the equations come from the even closed walks, other than the linear ones. So if you get rid of the linear equations, you're left with the equations of the fiber cone. And those even closed walks all give you beautiful binomials that are a Grubner basis. You can pick off the first terms, you get this hypergraph, and it's very nice to be able to see the depth that way. Another example is binomial edge ideals. So you start with a 2 by n matrix, and you form selected 2 by 2 minors. So if x3 is connected to x7, you form the minor using columns 3 and 7. And there is a way to figure out the Grubner basis, multiplying those generators by various paths in the graph that is a Grubner basis, and you can play the same game. So those were the other two examples I'd shoved into the end of the talk, but I'll tell you they exist and stop because I'm out of time. And out of chalk. Got down till it's too small to hold. Yes? Mm-hmm. In my mind, I had computations? Yes, I did. Mm-hmm. So for the binomial case, for the three cases at the end, it's easy to do for examples, and we just have run out of time to do it for classes. We were right there, and that got pushed. We have a scheduled discussion with Ty and Louisa and I to start doing that with classes, but we ran out of time. But that's the next thing on the list. But the original, we were actually looking at powers of edge ideals and trying to look at associated primes. So you can actually use this bound for powers if you start with a tree and skip the leaf pairs and just use the stars. So then the number of stars is a bound for R mod I. As you go up the power, every time you go up a power, you have to drop the bound by 1. Now there's an already known bound for trees that only drops by 1/3, but it starts with 1/3 of the diameter. And so this starts higher and drops faster, and that one starts lower and drops slower. We haven't gotten there yet. This is fairly new. It's not published yet. It's in the referee process. So very new. Yes. Mm-hmm.
You wrote that if you have an initially irregular sequence on R mod I,
Mm-hmm.
of length say R,
Mm-hmm.
then the depth of R mod I is bounded below by R.
By R, yes.
So we define as well the maximum length of initially irregular
Mm-hmm.
sequence, which we might call initial depth.
Initial depth, absolutely.
So, but even so, can you have a strict effort there?
Yes. There's actually, if you look in the paper, there's an example where we have an initially regular sequence of length 2. And if you just look at the next step and don't take the initial ideal, it's very easy to find a regular element, and the depth is actually 3. But if I take R, I1, F1, initial ideal, F2, if I take that next initial ideal, I get something that's M primary when I take that initial ideal. And so there, the initial depth would be strictly less than the actual depth.
So would it be interesting to characterize a quantity?
Sure.
Special?
We are still trying to figure out why most of the time these initially regular sequences are regular, and sometimes they're not quite. And I suspect there may be something there about when things work really, really nicely, that's when you're actually getting a regular sequence. And I should mention, not only are these regular sequences, they're about as nice as you can get. They're all linear. I mean, these are hyperplane sections. These are beautiful elements. Okay. And now I'm really out of time, even for questions. Okay. Thank you.